Welcome to Constrained Optimization by Noah. You have a surface. You want to know the maximums and minimums, those extrema, but you only care about points with an xy coordinate that is on this curve. This curve defines your domain. Only ones on the curve, not inside, not outside, just on the curve. How do we figure out those extreme values? Well, we're going to look at the contour diagram. So, here is y and x. Here are a bunch of different contours of our surface. And then here is our boundary. And let me draw some more contours. I can't fit all of them in, but it's like this. So, these are just some of them, right? Any point where the contour intersects is a point that is on this surface that has an xy point that is on this curve. So that's like a contender, but we only want the most extreme ones. What are the most extreme points? Those are going to be those points where the contour is tangent to this boundary. That's kind of where the surface is just reaching the boundary. So you can imagine it's going to be either the lowest or the highest point. Those most extreme points are where this curve that defines our domain, just the curve, that is tangent to the contour. So now, how do we find points where the contour is tangent to this boundary curve? Well, we're going to use a fact about the gradient. Let's say that let's say that our surface is defined as f of xy equals z. That's our curve. It has some gradient, f. And we know that the gradient is perpendicular to a contour. So let's say that this point right here, I'll just focus on that one. That point is going to be x0, y0. There is some gradient like this, and it's going to be perpendicular to that point. Now, we can also define our curve as if it is a 3D function, this boundary. We can say this is going to be g of xy equals some constant k, because it's 2D, but we'll write it like a 3D function equaling a constant. This also has a gradient g, and at that point, it will also, say it's like that, it will also be perpendicular. So, at this point, where this boundary is tangent to the contour of our surface, their gradients will be basically pointing in the same direction, or they might be kind of opposite essentially, but they're collinear, which means we can say that at this point, the gradient of our surface f is equal to, and here's the third color, some multiplier. And we use lambda because why not? It looks cool. We love Greek letters. Some multiple of the gradient of this kind of function defining our boundary curve at this point. Woo! That was a lot, very fast. Recap, we have a surface. We want to find, looking only at the points that have an xy value on this boundary curve, which ones are the most extreme. The most extreme ones are going to be the ones where this boundary curve is tangent to the contour of our graph. How do we find those points where our contour graph is tangent to our boundary curve? Well, we're going to know that at a contour, the gradient is perpendicular. So that means the gradient of both of these have to be both perpendicular to the same point, because these are tangent. And so we can say that this gradient is equal to a multiple of this gradient because they point in the same direction. That is the background of where this freaking equation came from. Now that we have this, we can use this to solve for this point. This point, x0 or x0, y0, is the extreme point, the extrema, at least the xy coordinate, that we are looking for. So, now that we have the conceptual down, let's go into the actual, useful stuff of how the frick we're going to use it. So, what do we do with this? Well, I'm going to write this as f of x, or like the partial derivative of f with respect to x, and I'll just label this f, and y. This is going to be equal to some multiplier times gx gy. And what I can do is I can make a system of equations by setting these components equal. You can also think, like vector stuff. We love vectors. So the x component of the f gradient is going to be equal to the multiplier times the x component of the g gradient. Same for, oh my god, I'm literally turning into her. I can see why she keeps them uncapped now. It's really convenient. The y component will be equal to the multiplier times the y component of the gradient of g. And remember that when I say g, gxy equals some number, and this defines our curve. And this number will come in and be important later, because, I'm trying to think space-wise. Yeah, let's get an example. This is our system of equations. Basically, these will both be in terms of x and y. This is an x and y. So we're going to have three variables. We're going to have x, y, and lambda. But we have two equations. We can't solve that. So we need a third equation. And that third equation, let this be an actual variable, will be our boundary equation. So now we have three equations from this. And we just need to solve that for x and y. And those x and y will be the x and y of our extrema. So this is the gross, awful part where it's just a nightmare because they give us such hard functions. What I like to do is isolate lambda in each of these, and then you set them equal to each other. So then you have two equations of just x and y, and then you solve that system of equations. And then once you have x, y coordinates, you plug them back into your original surface equation to find the z, the height. And yeah, after this, I am going to do like a problem of how to do this. Yeah.